Aguina Ushragus Accordia, is Mishon Tullav Paudra Gorgaira, Uchtron Akativ Riog na Hearn, Agus Tan Osor and Falcha Kurov Galer Gudian Chakan Agativ in you. Good evening, everybody. My name is Pat Gyrey, and it's my privilege and honour to be President of the Royal Irish Academy, and it's a great pleasure to welcome you here to Academy House this evening for the 2025 Hamilton Lecture. Quick show of hands, how many people here into Academy House for the first time? Quite a substantial number, including our visiting speaker. Good. So we've had, that's about a 25% call in. That's great. And now you probably all know where Café on Seine is, but actually Academy House is directly opposite Café on Seine. So we've been here since 1852, and at that stage when we moved in, this was a detached house on Dawson Street, and where we're sitting just now was the back garden, right? So the library and this meeting room since then has been built upon, and originally for an exhibition space. So you're very welcome to this, I would say, the most outstanding meeting room and lecture venue on the island of Ireland for this spectacular Hamilton lecture this evening. So I'd like to particularly welcome Professor Kip Thorne, our Hamilton speaker, who has travelled all the way from the very beautiful Pasadena, the Caltech, California Institute of Technology, to be with us today to deliver the Hamilton lecture. And earlier today, he facilitated the Hamilton Masterclass with this year's winners of the Hamilton Prize in Mathematics. So tonight's lecture, and indeed all of the Royal Irish Academy's Hamilton Day activities, are made possible thanks to the generous support from IBEC, who've been our partners on this flagship event for the past 6 years. So thanks to IBEC for that. Why are we gathered here on this particular day? Well, we're marking the date of 16th of October, because on the 16th of October 1843, the Irish scientist and then President of the Royal Irish Academy, and yes, you may feel that standards have slipped since then, but Sir William Rowan Hamilton discovered quaternions while walking along the Royal Canal from Dunsink Laboratory to an Academy meeting. Each year, the Royal Irish Academy commemorates Hamilton's contribution to mathematics by celebrating Hamilton Day. We do this because Ireland has a rich history of scientific excellence that should be celebrated and indeed recognised. And perhaps we're not good enough at doing that either, but let's have a good start with this. Although we look to the past to commemorate Hamilton's achievement, this event is also an opportunity to look to the future and to recognise the next generation of great Irish mathematicians. So earlier this afternoon, we presented the Hamilton Prize in Mathematics to the top students of mathematics in their penultimate undergraduate year, as nominated from 9 higher education institutions across the island of Ireland. If any of those are here today, will you please raise your hand so we can at least identify them? Put them right up. You should be very proud. Great, well done. So at that event, we're also honoured to host the Minister for Further and Higher Education, Research, Innovation and Science, Minister James Lawless, TD, who delivered a thought-provoking keynote speech. Thank you again to our sponsor IBEC for their continuing support on Hamilton Day, and the IBEC Chief Executive Officer Danny McCoy, who's seated here in the front row, and colleagues who've joined us here today, also from IBEC, and kindly hosted this morning's masterclass for the prize-winning students. Thanks also to our media partner for Hamilton Day, the Irish Times, who promoted the Hamilton Lecture in their paper and printed an interview with the Hamilton speaker written by Claire O'Connell, who I think is also in the audience. And this interview, which was on today's printed version with Professor Kip Thorne, came out earlier this week and makes for a fantastic read. So if you've not read it already, please do so, but not during this lecture. I will now hand over to our chair for this evening's lecture, Professor Sinead Ryan. Sinead is Professor of Theoretical Higher Energy Physics at Trinity College Dublin and has recently taken up the post of Dean of Research there. She has held visiting professorships in the USA and in the EU and is a life member of Clare Hall, Cambridge. Professor Ryan was elected to the Royal Irish Academy in 2023. And without any further ado, I will hand over to Sinead. Gorf Míle Maith Agat.
So good evening, everyone. It is a great pleasure for me to have the honour to introduce to you our speaker this evening. It's a real pleasure, actually professionally and personally, to introduce somebody whose name I have known for my entire career. So I first became aware of Kip Thorne. Actually, when I started my master's thesis, which was a long time ago, we won't go into that, but as a master's student at UCC working with Neil Muraku, who some people in the audience might remember. And Neil advised me to find a copy of Gravitation. He said it's the textbook you need, it's the comprehensive guide to everything you'll need to know for your master's thesis. And the authors of that textbook were Misner, Thorne and Wheeler. So I knew Professor Thorne by his surname first. Actually, to be perfectly honest, it was by the first initial of your surname, because the book was colloquially known as MTW for Misner, Thorne and Wheeler to those of us who were using it frequently. Neil also advised me, when he recommended your textbook, he advised me to also get a very sturdy backpack, because if you've seen the book, it's quite a tome, and so carrying it around the campus was no easy task either. Let me say some words about our invited speaker, our Hamilton lecturer for this evening. When I spoke earlier to Kip, he said, just say it's Kip. But I think, although he needs really no more introduction, I think I'd like to say a few words to set the scene for you and to give you a flavour of his impact and his extraordinary career. Maybe let's start where he is now. So he is the Feynman Professor of Theoretical Physics Emeritus at Caltech, as our president has said. And from 1967 to 2009, he led a research group at Caltech focusing on relativistic astrophysics and gravitational physics, and that group had extraordinary seminal contributions to the field. But perhaps I think you'll know Kip Thorne mostly for his enormous impact in leading the way to found the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. And LIGO made, of course, a huge breakthrough, observing for the very first time gravitational waves in September, I think, of 2015. And so for this huge contribution to science, Kip, together with colleagues, was awarded the Nobel Prize in Physics in 2017. He has many awards and prizes, you won't be surprised to hear. And if I were to start to tell you about all of them, well, then I would take up the hour that you really want to spend listening to his wonderful talk. But let me just mention a few for you to give you a sense of his global impact. He has been awarded the Shaw Prize, the Kavli Prize, the Special Breakthrough Prize in Fundamental Physics, and the Einstein Medal, to name, as I said, just a very few of those awards and recognitions of an enormously impactful career. Having said that, in 2009, actually, he decided to refocus and stepped away from his role as a professor of physics in Caltech and moved towards a career which was much more engaging with arts and located at the interface of art and science. And you won't be surprised to hear that there also he has huge enduring impact. So his career to date in this new era has led to a recent book, The Warped Side of Our Universe, and echoes in the title of his talk today. And here in this book, he interweaves poetry and art to bring to life scientific concepts in a beautifully unique and hugely memorable way. He was, of course, also very involved in the cult classic, the blockbuster Interstellar. And that movie really came from a concept developed by Kip and colleagues and a treatment of science in that movie that is really a testament to his imagination, but also his scientific rigor, I think. He was the executive producer and the science advisor for that film, Interstellar. He's currently working on a book, The History of LIGO, which I'm sure will be hugely interesting for everybody when it's available. Tonight, then, his lecture, as I've said already, speaks to his contributions at the interface of art and science. It's titled My Romance with the Warped Side of the Universe. He will guide us through his more than 50-year career, hugely impactful and hugely significant career, exploring the warped side of the universe, gravitational physics, but with a focus on mathematical rigor and the importance, the seminal importance and foundational importance of the laws of physics in his work. I think he'll also reflect on the transition from theoretical physicist to artist or artistic theoretical physicist, and talk us through what it means to make that changing career, and also what it's like to engage in collaborations across disciplines with artists and filmmakers. I'm really looking forward to this talk, as you can probably tell. Kip will speak for about 60 minutes, I think, so we'll have the pleasure of listening to him for about an hour, and then we'll have some time for questions from the audience after that. So please join me in welcoming this year's Hamilton lecturer, Professor Kip Thorne.
Can you hear me? That's a precise quotation from Stephen Hawking. He's a very close friend. That's how he began every lecture his entire career. It's a great honor to be here to deliver this Hamilton lecture, and I thank the Academy very much for inviting me to do this. In 1962, I moved from Caltech, where I had been an undergraduate student, to Princeton University to learn about general relativity from John Archibald Wheeler. I went to Princeton to work with him because John Wheeler was by far the greatest guru of relativity theory of that era. And from Wheeler, I learned that there is what I nowadays call, we didn't use this phrase in that era, the warped side of our universe. That is, objects and phenomena that are made not from matter like you and I, but rather made from warped space and time. Examples are black holes, gravitational waves, the Big Bang in which the universe was born, vacuum fluctuations. That's not one that you normally hear associated with this, but I'm going to go into some detail to explain why you inevitably cannot avoid a major role of vacuum fluctuations on the warped side of our universe, and wormholes. And I want to begin by describing the great richness of the warped side of our universe by discussing in detail the aspects of black holes that are made from warped space and time. So let me begin by showing from the movie Interstellar. Interstellar's black hole Gargantua. At the time that the movie came out, I think people were rather amazed that this is what a black hole looks like. So let me explain why this is what a black hole looks like. If you have a black hole in the astrophysical universe, these black holes are often surrounded by what we call accretion disk of hot gas, rather similar to the rings around Saturn. In this case, we have a thin disk in the movie that is a gas that is spiraling around and around the black hole, gradually spiraling into the black hole. And as it goes in, friction makes it hot. And there's a IMAX camera there, just by chance. And a light ray from the upper back face of the disk goes up and over the black hole, being pulled by the hole's intense gravity and down to the camera. And that, not surprisingly, makes this upper part of the image. That's just the image of that face, but brought down along this light ray from above. And similarly, a light ray from the bottom back face goes under and up and makes the bottom part of the image. And a light ray from the front of the disk heads out to the camera and makes the crossbar. So it's all very, very simple. However, in 2019, a great new telescope, which was really the combination of data off a number of radio telescopes, called the Event Horizon Telescope, observed for the first time the black hole at the center of a galaxy, the black hole of the galaxy M87. This is a collaboration of 400 scientists and engineers at 100 institutions led by Shep Doleman at Harvard. And they took these radio telescopes and many others at these locations around the world, and they combined the data coherently, working at a radio wavelength, well, really a millimeter wavelength of 1.3 millimeters. And by that coherently combining those data, they made this image of the black hole in M87. And knowing how far away the black hole was and how large this shadow of the black hole is, they were able to deduce that this black hole weighed about 6 billion times more than the sun weighs. Rather remarkable. Now let's compare the Gargantua which was what we had in the movie, with what was observed. Now, many people have commented how similar these are, but no, they're not similar at all, let's be honest. They don't look at all alike. Now, why don't they look alike? Well, my colleague Oliver James at DNEG, Double Negative Visual Effects, he and his colleagues there got the Academy Award for the visual effects in the movie Interstellar. He made this little video to explain what's going on. So here you see the black hole Gargantua as it would be seen with a camera near the equatorial plane of the black hole. But let's just move the camera up to the North Pole and see what happens. Move it up to the North Pole, and of course, that's what it looks like. And then you smear out the image because the astronomers don't have anything like the resolution that we had in the movie. And my goodness, that's what it looks like. And except that it's lopsided. Now, why is this lopsided? Why isn't the image in the movie Interstellar lopsided? Well, the answer is I argued with Christopher Nolan, the director, about it's got to be lopsided because the gas on the right-hand side is moving toward us. So there's a Doppler shift which makes the light brighter than the gas on the other side, which is moving away from us. And so it's got to be lopsided, I said to Chris. And Chris said, no. Be realistic, come on. The human eye is incapable of distinguishing levels of brightness or even colors when you have something that is as bright as this accretion disk. And we are going to be accurate with regard to what the human eye would see. And so I threw in the towel. He was right, and I was wrong. And so it is as we showed it. Now, the black hole is made from warped space-time, as I said. What does that mean? Well, it means, for example, the circumference around this black hole is much smaller than the diameter. And how can that be, you might ask? Well, a little analogy explains it. If I take a child's trampoline, a sheet of rubber, I put it up on very high stilts, and then I put a rock at the center so the rubber bends down like that. And if I then, I am an ant, and I go marching around here and I measure the circumference, and then I go to measure the diameter. Obviously, I measure a far greater diameter than circumference. And so it's all very simple. That very same diagram really explains what's going on with the black hole. With the black hole, if I take an equatorial slice, a two-dimensional surface through the black hole, and I want to visualize the warped space around the black hole, well, I have to then embed it in a higher dimensional flat space, like what we had here in this picture, in order to visualize it. And so I embedded in a higher dimensional flat space, which physicists would call the bulk, but Christopher Nolan calls the fifth dimension in the movie, because time we all know is the fourth dimension. So if you got one more dimension in this higher dimension that is not part of our universe, but we're looking in from that higher dimensional universe from the fifth dimension, then this is what it looks like. And in place of the rock, there is a singularity, and I'll return to the issue of the singularity in a few minutes. But just there's something there that is very different from a rock, and that is actually a place where the laws of physics, as we understand them, break down. Now, what we all know about black holes, the most famous thing is if you fall in, you can't get back out. If you fall in, you can't get signals back out. So here I am. I have a microwave antenna. I'm sending signals back out to you on the outside. When I cross through the surface of the black hole, which we call the event horizon, or just the horizon, thereafter, I and the signals get pulled down toward the singularity at the center. And the signals can't get out, and I can't get out. And so that's the famous thing about it. But we can understand that also from a different point of view when we recognize that not only is space warped around the black hole, but so is time. As you go down near the horizon, and if you try to hover there, you'll find that time slows compared to time back here on Earth or up at high altitude. And in fact, in the movie, it's an extreme slowing of time. There's a planet that is near the horizon in the movie, Interstellar, And 1 hour on that planet, called Miller's planet, is 7 years on Earth. It's an extreme slowing of time. But if you go beneath the horizon, time then, what happens to time? If time slows to a halt at the horizon, then what can time do beneath the horizon? The answer is time flows downward in a direction you would have thought was a space direction toward the singularity. I like to call that down cascading time. It's basically flowing downward. And that's another reason that nothing can get out of a black hole, that you cannot move backward against the flow of time, the local flow of time. That may be that it's possible to go backward in time, but only by going out into the universe and returning before you started. You cannot locally move against the flow of time. It's just absolutely, totally impossible, the laws of physics tell us. In addition, a black hole spin, and as they spin, they drag space into a whirling motion, like the air in a tornado, with high angular velocity near the horizon and low angular velocity farther away. Now, these are my own hand drawings. Now let me show you what the actual warping of space and time looks like, according to Einstein's relativity theory, for a black hole that is a real black hole spinning rather rapidly. So for a fast-spinning black hole, this is the shape of space. It's sort of like a trumpet horn. Down here is the horizon. The horizon looks like a circle, but remember I have removed one space dimension. This is just the slice through the equator of the black hole. If I restore that space dimension, the circle becomes a flattened sphere. That's the horizon, is just a sphere, a spherical hole in space. The color coding is the slowing of time. Where it's yellow, time is flowing at 10% the rate far away. And the arrows, the white arrows, show the angular velocity of dragging of space into whirling motion, fast near the horizon and slow farther away. And this is the bulk, of course. This is what the black hole looks like from the bulk, from the higher dimensional space, which may or may not be a fictitious space. We don't know. There may actually be a bulk there. It's quite possible it really exists in reality. Now, what warps the black hole space and time? The answer is the energy contained in the warping. A black hole is held together by nonlinear self-interaction, are the words we use in physics. So it is what is sometimes called a gravitational soliton. Now, a technical remark for mathematicians and physicists. I'm going to explain something about the warping of space and time around a black hole. And others, people, you're not a mathematician or physicist, just ignore the next minute of my conversation. But I want to explain something that is not terribly well known, because it's a new insight that comes, that's only about 10 years old. In vacuum, where you have nothing but warped space-time, choose a local reference frame. And then decompose the Riemann tensor. This is the thing that actually describes the warping of space and time, the curvature of space-time. Decompose the Riemann tensor into its irreducible tensorial parts. This is jargon that has precise meaning to mathematicians and physicists. The irreducible tensorial parts turn out to be two symmetric trace-free tensors, the tidal field and the frame drag field. The tidal field describes a stretching and squeezing of space. The frame drag field describes this whirling motion of space, but a differential whirling, fast near the horizon and slow farther away, or a differential precession of inertial frames, to be more precise. So just keep that in mind, those of you who are mathematicians and physicists. That's going to play some role as I go. And the place where you can go read about this, since it's not in other textbooks, is my own textbook with Roger Blandford, a rather recent textbook, in particular boxes inside there that you read all about that particular mathematics. Okay, having said that, let's talk about the whirling motion, the dragging of space into a whirling motion. if I put my wife up here just above the black hole, this is really Leah Halloran's wife. Leah Halloran is the painter that I have written this book with, and I'll refer back to a number of times in this lecture. So this is really Leah's wife, so I'll put Leah's wife Felicia above the North Pole of the black hole. If she looks down at her feet are closer to the black hole than her head, and so she sees her feet whirling around counterclockwise faster than her head. But if her feet look up at her head, her feet see her head whirling around counterclockwise. It's like if you take a wet towel, you try to wring out water. If your left hand sees your right hand going counterclockwise, then your right hand will see your left hand going counterclockwise. So there's a counterclockwise twist in the towel. In this case, there's a counterclockwise twist in the whirling motion of space. And this is what arises from this frame drag field, again, for the mathematicians. And there's a precise, then, description of that in terms of this frame drag field. There's a counterclockwise vortex sticking out of the North Pole and a clockwise vortex sticking out of the South Pole, it turns out. So remember, a spinning black hole has two vortices of twisting space. They're made from warped space-time, sticking out like my arm sticking out of my body. But they're not made from matter, they're made from warped space-time. And let me talk about tidal gravity. This is the other piece of the Riemann tensor for the physicists. We usually talk about this in terms of the moon raises tides on the Earth's oceans, and it's the side of the Earth that's closer to the moon, the gravitational pull is stronger, and so it pulls harder and it raises the tide. And on the far side, basically the Earth is being pulled harder than the ocean there, and so the far side is sort of left behind as the Earth gets pulled up. It's better to look at this from the Earth's own point of view, freely falling. And then if you just subtract out the gravitational pull on the center of the Earth, then what you have is a stretching and a squeezing on the Earth's oceans. So that's the standard story we give students in physics and astronomy about how the tides come about. But there's another point of view, and this is due to the so-called tidal field that I just explained to the physicists and mathematicians. This is the way I think about it. The tidal field has what are called tendices, or there's a stretching tendex that stretches toward and away from the moon, and a squeezing tendex that squeezes in the circumferential direction. And that is the physical manifestation of this tidal field, the second piece of the Riemann curvature tensor. In the movie Interstellar, it's the planet, Miller's planet, and the black hole is producing the tidal field, and it is stretching and squeezing Miller's planet in just the same way. What goes on inside a black hole? Well, in the movie Interstellar, Cooper, the hero in the movie, finds out. He falls into the black hole. I'm going to show you a famous segment out of that movie as Cooper plunges through Gargantua's horizon riding in the Ranger spacecraft.
Approaching the horizon.
So he's just outside the horizon of the black hole. You see behind him, you have in front of him, he's going down in that direction. Here is the black hole below him. This giant, it's now becoming a very giant black region, which is the interior of the black hole he's trying to look into. And out here is the external universe. Now let's remember that the external universe is on the right, the black hole is on the left. Now he's going to keep going, and you'll hear him talk about going through the horizon.
Port side, dipping down beneath it. Go through it.
Now notice what has happened. That's the external universe. The disk, the accretion disk that is this ring of the accretion disk was like that, but now it's like this, and the external universe above him is getting squeezed into a little circle above his head. And the black hole is coming to subtend a very, very large fraction of his sky. This is what it really looks like. We made sure that in this movie that the visual effects really reflect what is going on, and what you would see if you fall into the black hole. And after he falls into the black hole, he encounters singularities. There is a chaotic singularity down here. He's headed toward this. This is a place where the laws of physics fail. They fail in a wild way, where the stretching and squeezing of the tidal forces become very dynamical and chaotic, and that is not something he wants to encounter. However, there's another singularity. That's for physicists called the BKL singularity. Time is so screwed up inside here. It is so compressed that everything that falls into the black hole in the billions of years of the rest of the life of the universe behind him comes crashing down in a thin sort of shock wave that is it's all called the infalling singularity. And he has this massive singularity of everything that falls into the black hole after him coming right down on top of him very, very quickly as seen by him. It's really weird. This is what physicists call the mass inflation singularity. But there's also an outflying singularity. Everything that fell into the black hole in the past lifetime of the black hole, a little bit of it is scattered back up and is smashed into a very thin layer. This is another singularity where the laws of physics fail, but a much more mild singularity. And his goal is to encounter the outflying singularity, which he can likely survive. And he does. That's what he encounters, is the outflying singularity. Physicists sometimes call this the shock singularity. And it is there. Now this gets wild, but this is based on a speculation about what the laws of physics say goes on in the bulk. There's a higher dimensional civilization that has built a spatially four-dimensional spacecraft called the Tesseract. It's a cube in 4 space dimensions that catches him as he nears this outflying singularity, carries him up into the bulk and back to Earth. You don't know that that's what's happening, but that is what happens in the movie. Christopher Nolan and I worked very hard on the ending of this movie. Chris said to me when we first started working on this movie, he said, I wanted an ending that is as mysterious as the ending of Stanley Kubrick's 2001 A Space Odyssey. And he got it. We agreed that the only way that you will ever know what's really going on in the ending is by my book. And so I wrote a book, The Science of Interstellar, and chapters 27 through 31 explain the ending of the movie. I'm not going to say anything to you about what the ending really is. But the key thing that I had done for you is I've used this as a tool to explain what goes on inside black holes, to explain that the black hole has all these features that are made from warped space and time. And so in this book with Leah Halloran, my co-author, she's the painter, I attempt to be a poet. I am now going to, in a video made by Paula Froley, a friend of ours, from Leah's paintings, and me reading my verse, I'm going to tell you what a black hole is. But I'll begin by telling you what Leah's wife, Felicia, is, so that you understand what I mean by what is, and then I'll tell you what a black hole is. So let's go. What is Felicia? She's the sum of all her parts. Her face, her silken hair, her arms and breasts, her hands and legs and feet, her heart, her brain, her precious personality. And what is a black hole? It's the sum of all its parts. Its space that is warped, the funnel of bulk being seized, its vortices of whirling space, its tendencies that stretch and squeeze, its slowing time and down cascading time, its horizon and its singularities, all made from warped space-time. Okay, so that is then intended to give you some sense of the enormous richness of phenomena that you can have that are made from warped space-time that you do have in the case of a black hole. And then for the physicists and mathematicians, how does it arise? Well, through these decomposition of the Riemann tensor into these two pieces, the tidal field and the frame drag field, which then when you investigate them mathematically and through computer simulations and analytically, you see all of these structures there. Okay, so let me move on then. So let me turn to gravitational waves. Albert Einstein in 1916, from his newly developed general relativity theory, he made the prediction of gravitational waves. And what these gravitational waves are is shown here. We have an array of freely falling particles out in space. The gravitational waves are propagating into the screen, and the gravitational waves are made from Tendex lines that stretch horizontally and Tendex lines that squeeze vertically, and then the stretching and squeezing oscillates. And so the red Tendex lines fade out and become blue, the blue Tendex lines fade out and become red. I'm not showing that change of color. All I'm showing is the consequences of the stretching and squeezing of space like that. Now, another way to say it is that if you have inertial reference frames here and there, and you have these particles which are insisting on remaining inertial, there are no forces acting on them other than they're being forced to basically remain inertial. So you have a local inertial frame here, a local inertial frame there. Those inertial frames are moving back and forth relative to each other. And that's another way to say what the gravitational wave is doing. Just to make it explicit, a Tendex then is a collection of Tendex lines of this sort. And there is a precise technical meaning of Tendex lines and how they arise from the mathematics. Now, there are only two types of waves for exploring the universe as far as we can tell. They are electromagnetic waves, light, radio waves, X-rays, gamma rays, and gravitational waves. And it was Galileo 400 years ago who built a small optical telescope, pointed it at Jupiter, and discovered Jupiter's 4 largest moons, and in the process initiated instrument-based electromagnetic astronomy. And in those 400 years since Galileo's time, this form of astronomy has burgeoned with not just light, but radio waves, X-rays, gamma rays, and so forth, all forms of electromagnetic waves in the frequency bands that can travel back down to Earth that we can measure. Using the electromagnetic astronomy, astronomers have completely changed our understanding of the universe. It's just totally revolutionized. Our understanding of the universe is so different today than it was in Galileo's time, thanks to these observations. And so in 1972, my colleagues and I had a vision that we wanted to create gravitational astronomy. We wanted gravitational wave astronomy. We wanted to do for gravitational waves what Galileo had done for electromagnetic waves. And we thought that the technology was maybe going to be good enough for us to be able to do it in our lifetimes. Ray Weiss, a colleague of mine at MIT, whom I knew from my graduate student days at Princeton, we'd become good friends. He sent out to me and his other colleagues at other institutions a technical paper proposing a type of gravitational wave detector quite different from anything others had really thought about. And in this technical paper, he analyzed all of the major noise sources that this gravity wave detector would face and proposed ways to deal with them, did calculations to see just how low you could drive the noise by the methods that he was proposing, and therefore through these calculations, he estimated that if you built something like this that was a few kilometers in size, you had some possibility of success. And so the nature of this detector was you hang 4 mirrors from overhead supports. When the gravitational waves come along, they push these mirrors apart and push those mirrors together. But you make sure that the distance between the mirrors is a half integral number of wavelengths of light. So light can resonate in here. It goes down, comes back, and then when it comes back precisely in phase with the light when it's set out. So light would be trapped in these mirrors, and then it would you build up a very high intensity. Actually, in these detectors today, intensities of hundreds of kilowatts of power circulating in the arms. The light would go back, interfere at the photodetector, and you get a signal toward the photodetector, interfere in this beam splitter, and you would get an intensity going into the beam splitter that rises and falls due to the differential stretching along this arm and squeezing along that arm that the gravity wave makes. So this is familiar to physicists and mathematicians in the audience. And it is just an ideal way to try to detect these gravitational waves. I have to say, I was totally skeptical for several years that we really had any chance of success by this method, but I became convinced after really looking at it in depth. And so I wound up spending a large fraction of my career helping Ray Weiss and his colleagues build these things and ultimately having success. Now, gravitational waves are made from the same thing as black holes, from warped space-time, so they are the ideal tool for exploring the warp side of our universe. So after 43 years of intense work from the time when he proposed this, developing and perfecting Ray Weiss's gravity wave interferometers as elaborated with ideas from Ron Drever and others who improved on Ray's original design. This is Ron Drever, who made these major contributions along with Ray Weiss. A 1,000-person team called the LIGO team for Laser Interferometer Gravitational Observatory organized, assembled, initially led by Barry Barish, designed and built gravity wave interferometers, we call them. Gravity wave interferometers are these gravity wave detectors. And the team developed data analysis techniques. And another set of people who are experts in computer simulations developed the tools for simulating on computers collisions of black holes by solving Einstein's equations numerically, called numerical relativity. After 43 years of effort, and I'm summarizing then in 1 or 2 minutes, 43 years of effort, $1 billion of taxpayer money, several thousand people who contributed to this effort. On the 14th of September 2015, the first gravity wave signal came in to LIGO from colliding black holes. And this is a visualization of the thing that produced then the first gravity waves that we saw. You see 2 funnels like that. You're looking in from the bulk. And so each black hole is like a funnel, so the diameter is big compared to the circumference. The red color is the slowing of time near the horizon, and the arrows are the dragging of space into motion, but these black holes are not spinning, and so there's no whirling motion around the black holes. The black holes, I'm going into slow motion. In the moment of the merger of the black holes' horizons, there's a gigantic splash in the shape of space, and then an oscillation in the shape of space and the rate of flow of time, oscillating back and forth, producing gravitational waves to go traveling out into the distant universe, carrying information about the collision. And this is what was seen. Now, I've told you that there's a lot more structure to black holes than just the shape of space. There's all these other things. And so Leah Halloran has kindly drawn this painting that explains the other things that we know. When the two black holes suddenly collide, there are tendencies that stretch sticking out of the ends here and out of the ends there. Those are the loose tendencies. And then there are tendencies that squeeze going around. And coming out of the merger region, there's tendencies that squeeze sticking out, tendencies that stretch going around. And as the black holes tumble, because they were orbiting around each other, these tendencies swing out like water from a twirling sprinkler head, like water from a twirling sprinkler head. And they go flying out into the external universe. They become the gravitational waves that LIGO sees. And so there's this great initial stuff going on here that you don't see in that movie. In addition, there's a second family of, let me just go back here to, there's a second family of gravitational waves. They're generated in this way. Each black hole is spinning, at least a little bit. And so there are vortices of twisting space sticking out of each black hole. We're now looking at, in this case, from the higher dimensional bulk in order for me to explain what goes on. And so you have these vortices of twisting space that swing out like that. And then there's a remarkable thing that these outflying vortices, as they move outward, generate entwined tendencies that stretch and squeeze. And so that vortex, as it moves outward, it creates these tendencies which become the gravitational waves. It's really quite an amazing thing that happens. And again, for the mathematicians and physicists, the Bianchi identities of general relativity, in fact, look very much like the dynamical Maxwell equations. The time derivative of the tidal field, which is the time derivative of these tendencies that stretch and squeeze, minus the curl of the frame drag field, which is a measure of the vortices, is equal to 0. And as you know, in Maxwell's equations, a moving magnetic field generates an electric field. And what's going on here is that the moving vortices generate the surrounding tendencies. And the mathematics is almost exactly like what happens in Maxwell's equations. And it is really interesting that we didn't really understand this until, driven by the need to be able to compute the shapes of the waves for LIGO data analysis, a team they called the SXS team of numerical relativity experts, they did simulations in which we saw this going on from the simulations. And then we saw it also analytically. And so it was just quite a remarkable thing. These discoveries are made driven by the effort to discover gravitational waves. Okay, these gravitational waves traveled out of the galaxy in which the black holes lived, into the external universe, across the great reaches of the external universe for 1.3 billion years. 50,000 years before, 50,000 years ago, these gravitational waves reached the outer edges of the Milky Way galaxy. That's 50,000 years ago when the Earth our ancestors were sharing the Earth with the Neanderthals. Just think of that. And this burst of gravitational waves then entered our galaxy, traveled for 50,000 years, and reached the Earth on 14 September of 2015 near the Antarctic peninsular tip. The burst traveled up through the Earth and emerged through the Earth at the LIGO Gravitational Wave Observatory in Livingston, Louisiana. And 7 milliseconds, 7/1000th of a second later, it emerged at the gravity wave detector in Hanford, Washington. And our detectors saw the waves. And our collaboration, our 1,000 people working in this collaboration, were just amazed at these waves. And it took about 4 months to be 100% sure that this was really gravitational waves and that, for example, somebody hadn't hacked us. And then we announced the discovery, and by comparing with the shapes of the waves, stretch and squeeze as a function of time, that were computed by the numerical relativity experts, the so-called SXS collaboration, with the incoming signals, we were able to deduce that these were two black holes merging. Initial black holes were 29 and 36 solar masses for a total mass of 65 solar masses. Final black hole was 62 solar masses. 3 solar masses went into gravitational waves. This is as though you had annihilated 3 suns and put all of the mass from those 3 suns into gravitational waves. And you had done it in a fraction of a second. So the total power output during that fraction of a second was 50 times larger than the total power output in electromagnetic waves from all the stars in the universe put together, but only for a fraction of a second. But that is just incredible. In gravitational waves, no electromagnetic waves whatsoever. And the distance was 1.3 billion light years from Earth. LIGO has now seen about 300 black hole collisions. It's been exploring the properties of black holes, the laws that govern black holes, the populations of black holes in our universe, and it's just a very, very exciting beginning of gravitational wave astronomy. And it has also seen several collisions of neutron stars, stars that are about 10 kilometers across, that weigh about what the sun weighs, that have central densities of about 10 times the density of an atomic nucleus. Several collisions of neutron stars, several black holes swallowing neutron stars. We are exploring the warp side of our universe with gravitational waves. Now, the holy grail of this field is, for as far as I'm concerned, is to explore the Big Bang birth of our universe with gravitational waves. And so I want now to move into the last piece of the talk, which is going to be another 20 minutes. I'm 40 minutes. I have a timer here. I'm 40 minutes into this talk, and so I need to squeeze this last bit into 20 minutes. The foundation for all I'm now going to say is these vacuum fluctuations that I advertise that you have rarely, even the experts here have rarely probably heard associated with warp space-time. So let me explain. It was Jakub Borisovich Zeldovich, one of my mentors, along with John Wheeler. I count Zeldovich as one of my other mentors who had a huge impact on me, who said that, who explained what I'm going to explain to you, that vacuum fluctuations are inextricably entwined with the warp side of our universe. So first I need to explain what vacuum fluctuations are. So let's take a box. And let's remove from that box everything that exists inside the blocks to the extent that the laws of physics allow. Now, if you do that, there still remain quantum mechanical fluctuations because of what's called the Heisenberg uncertainty principle. If we usually hear it saying that you cannot simultaneously know the position and the momentum or speed of a particle. But that means if you know, you can't simultaneously know the position and the speed of the particle. And if you know the particle is precisely at this location, then you know nothing about its speed, so you know nothing about where it's going to be a moment later. And this basically carried over more broadly into other things, basically says that there are always fluctuations left behind. If you remove everything that you possibly can be removed, you're left with tiny fluctuations of whatever could have been there is still remaining. So if it's light you're talking about, there are tiny fluctuations of light. We call these sometimes virtual photons. If it's electrons, then you have virtual electrons and virtual positrons flashing in and out of existence with some probability for high probability that there are, say, photons here and a very low probability over there. And so Leah Halloran has done this painting for me where you see the dark things, that's where there's a high probability of finding photons. In here, where it's much lighter, there's a very low probability of finding photons. And so this is all the time changing, this pattern of the probabilities in there, just continually fluctuating and unstoppable, totally unstoppable fluctuations. That's the nature of the world. You can't stop this. It's always there. And these are going to be central to my last 20 minutes of this talk. These fluctuations have basically no energy and produce no gravity. Essentially, by this, what I mean is, many of you are aware of the idea that there is a tiny acceleration of the universe, and that it may arise from some tiny remaining energy associated with so-called renormalization of these fluctuations. This is, again, is for the physicists and mathematicians. That is such a low energy compared to the things I'm talking about that I'm going to ignore it, okay? And so for all intents and purposes, these things have no energy. September 1973, I take Stephen Hawking to Moscow. And in the Hotel Rossiya, again a painting by Leah Halloran, in the Hotel Rossiya in Moscow, we meet with Yakov Borisovich Zeldovich and his student Alexei Starobinsky. Stephen Hawking I don't show myself. And Zeldovich and Starobinsky describe the following. They say, look, if you have a spinning black hole, there are always vacuum fluctuations that are bathing the spinning black hole. They're bathing from all sides, but Leah is only going to show them both bathing from the left because we want to explain what happens with the vacuum fluctuations. So they bathe the spinning black hole, and Zeldovich had guessed with very high probability of being correct, and Starobinsky, his student, had proved mathematically, using our best understanding of the laws of physics, that those vacuum fluctuations suck up energy from the vortices of twisting space around this spinning black hole and turn themselves into real outflying particles, real outflying radiation. So if there is no real photons coming in, no real electromagnetic waves, but real electromagnetic waves, real photons come off, it's as though the black hole is spontaneously creating electromagnetic waves, photons, that are flying off, but this creation is done by these vacuum fluctuations sucking up energy from the vortices of twisting space. That was a huge surprise to me. When Zeldovich first asserted to me, he told me a year earlier or so that this was the case. Starobinsky hadn't proved it. I thought he was crazy. And Starobinsky proved it, and it turns out to be absolutely right. And this is the key thing that I'm getting to, that if you have a dynamical space like this, vacuum fluctuations just they feed off of the dynamics. And they turn into real particles, and you just can't get rid of them. Okay, so this is what happened there. Stephen Hawking went home. He's a lot smarter than me. He thought much more deeply about this, and he realized, he had an epiphany in December 1973. If you have a star that is a spherical star that implodes, it creates a black hole at its center, and the black hole expands to eat the star. Then as it expands, the surface of the black hole is expanding outward at the speed of light relative to local inertial reference frames. And there's a sort of a stretching of space around the black hole, and that sucks energy from vacuum fluctuations and turns them into real particles that go flying off. And that is what came to be called Hawking radiation. And he told us, Stephen did, and my colleagues and I were very skeptical at first, but deeper analysis showed that he was absolutely right. That a black hole being born creates this Hawking radiation that keeps coming off for the rest of the life of the black hole until the black hole perhaps is ultimately evaporated. It was just incredible. And the vacuum fluctuations do it. So Zeldovich then had another epiphany. He said, and this is already going back to 1971, In the birth of the universe is born expanding, and so if it's born with no matter in it, only vacuum fluctuations, you can't avoid the vacuum fluctuations of light, vacuum fluctuations of particles, electrons, protons, and so forth. When the black universe is born with these vacuum fluctuations, surely they will suck energy out of the expanding space and create all the matter in the universe that we see. But he couldn't make it work. It just didn't work. He wasn't getting enough creation of stuff, and so it was a idea in search of something that was missing, and it was his student Starobinsky and Andrei Linde, also in Moscow at the time, now at Stanford, and Alan Guth at Harvard, with others contributing later on to various pieces, who realized that if in the very early universe the expansion of the universe was extremely fast, what we call exponentially fast expansion, what now is called the inflationary expansion of the universe, then that inflationary expansion is capable then of feeding enough energy into the vacuum fluctuations to produce all of the matter and radiation in our universe. And so this, for those of you who know about inflation, this is where it all comes from. And again, it's vacuum fluctuations that are responsible. And so that was really quite an eye-opener, and is one of the most exciting things in cosmology. Let me talk about wormholes for just a moment. Just very briefly, Albert Einstein and Nathan Rosen in 1935 conceived the idea of a wormhole. They found that what's called the Schwarzschild solution to Einstein's equations produces the Schwarzschild solution to Einstein's equations is a wormhole that may reach across between two distant regions of space. And so this again is going to interstellar. Here is the IMAX camera in interstellar. Here is the distant galaxy. Here is light coming through the distant galaxy, out of the distant galaxy, and up the wormhole, up the surface of it, because this is the bulk outside of our universe. We're just seeing the two-dimensional slice of our universe. And the light comes from the distant universe up this surface, similar to traveling along the funnel, when I talked about the funnel before, up to Saturn. And in the movie Interstellar, we designed the wormhole to produce the kind of image that Christopher Nolan wanted for the wormhole, and it looks just like this. But the problem with wormholes, and wormholes play a major role in the movie Interstellar, and John Wheeler, my thesis advisor, at about the time that I first met him, he realized that by digging deep into the laws of general relativity, that wormholes will pinch off so fast that nothing can travel across them unless you do something to hold them open. So a wormhole with nothing there to hold them open pinches off, creates singularities, and so all the dreams of Interstellar and Carl Sagan, all the other wormhole things done in Hollywood, just forget them. So then the issue arises, can a wormhole be held open? And the answer is, if you want to hold it open, you have to place in its throat something that repels gravitationally. This is what I call exotic matter. And it does turn out that you can create things that repel gravitationally. You take the vacuum fluctuations and remove them from this region, and let that region over there borrow the vacuum fluctuations. This region will repel gravitationally, that region will attract gravitationally. So if you're clever enough, you might be able to devise a way to to collect enough exotic matter in the form of vacuum fluctuations where you have removed from one region enough energy that it anti-gravitates, but there's some adjacent region over there that is gravitating. And so That, in fact, was first discussed in connection with Carl Sagan's movie Contact, which I helped him with. And so the issue is making exotic matter by manipulating vacuum fluctuations. You can imagine a very advanced civilization doing this. And this is highly speculative, but this is basically a high speculation that underlies the use of wormholes in Hollywood movies. So let me tell you the bottom line, because there's been a lot of work done by physicists trying to understand whether or not you can have enough exotic matter inside wormholes to hold them open. Again, I'm summarizing 40 years of research in what I'm going to tell you. Can wormholes occur naturally? Almost certainly not, except conceivably, well, it's fairly likely, as John Wheeler speculated, that quantum foam, which is the quantum fluctuations in the topology of space, wormholes fluctuating in and out of existence on a tiny scale called the Planck length, that there is such a quantum foam of fluctuations of wormholes, and you can imagine if you're a physicist and are a little drunk or a lot drunk, you can imagine a very advanced civilization grabbing one of these wormholes that's fluctuating in and out of existence and enlarging it to classical size. But as far as I can tell, that's the only way that you're going to get wormholes created by an advanced civilization in some technique like this. Can they be made by an advanced civilization? Possibly. Can they be held open? Probably not. It probably requires too large amounts of exotic matter. That's the conclusion of 40 years of research by theoretical physicists. But when speculating beyond the frontiers of firm knowledge, I've been proved wrong many times, sometimes spectacularly wrong, so don't take my pronouncements too seriously. Let me just move on to the very last piece of my talk. The very last piece of my talk deals with vacuum fluctuations in modern quantum technology. What is called quantum precision measurement technology. And this is a piece of the LIGO story that has been extremely important, as I will explain. Vladimir Braginsky, another Russian who was a major mentor of mine, a superb experimenter with whom I collaborated on and off over many decades of work, he realized that by whatever kind of technique that you might try to use to search for gravitational waves, you had to be dealing with the motions of big masses. So he made a general argument, which I think is a very good argument. And these big masses will necessarily have quantum fluctuations. And you're going to have to deal with those quantum fluctuations ultimately, because those quantum fluctuations of the big masses may hide the gravitational waves you're searching for. So he first said that to me in 1968 on my first visit to Russia. And I didn't fully understand what he was saying, but I came to understand it much more clearly. Let me just say, I spent a portion of my career translating Braginsky to the physics community, not translating his Russian into English, though I could do those translations with some effort, but translating his way of thinking about physics into the way that my colleagues and I usually think. And I did that with other people. A great mathematician, Demetrius Christodoulou. I spent a hunk of my career translating Christodoulou into physicists. So if you have a really brilliant person, they may have insights that are tremendously important, but they express them in ways sometimes that the rest of the physics community can't understand. So I translated Braginsky into physicist language, and the bottom line was the following: that LIGO, in the case of LIGO, the problem is the quantum fluctuations in the so-called centers of mass of these mirrors. And the centers of mass of these mirrors jiggle back and forth due to vacuum fluctuations or quantum fluctuations. And at the level that LIGO is now operating at, we have 40 kilogram mirrors being monitored with a noise level about 10 to the minus 19 meters, or 1/10,000th the diameter of the nucleus of an atom. And those quantum fluctuations of the centers of mass of these mirrors are at a level that they would be hiding the gravitational waves that we are now seeing if we didn't have a technology, quantum technology, to control those quantum fluctuations. So for the first time, we humans today are seeing human-sized objects, 40 kilogram mirrors, behave quantum mechanically. We always thought of atoms and molecules as the things where quantum mechanics operates, but no, it also operates on the scale of 40 kilogram mirrors, and we see it in LIGO, and we have to control it. And this is what is called quantum precision measurement technology today. Brzezinski called it quantum non-demolition technology. You want a technology that enabled you to not demolish a gravity wave signal when you're trying to get it through an instrument where the mirrors are shaking around due to quantum effects. Now, it turns out that it's a student of mine, Carlton Caves, first realized this story. Now, what I'm going to do is tell you about now some fantastic work done by this student of mine, Carl Caves, just as when he was completing his PhD. There are two quantum noises in these gravity wave interferometers. The first is fluctuations in the motion of the centers of mass of the mirrors. And we have spent hundreds of millions of dollars to isolate the centers of mass of the mirrors so that when we make measurements, we see the motion of the centers of the mass of the mirrors. We don't see the fluctuations in of the atoms in the mirrors. We're actually measuring the centers of mass of the mirrors. That's a big piece of the LIGO technology. And so there are quantum fluctuations of the mirror centers of mass. And there's random arrival of signal light in the form of what is called shot noise, random arrival of the signal photons at the photodetector. Those are two quantum noises in our instruments. And Carlton Caves had this tremendous insight in 1981 that both quantum noises are controlled by vacuum fluctuations of light entering the interferometer from its output port. That is, from the input port is where you send the laser light in. The output port is where you bring your signal out into this photodetector. Vacuum fluctuations coming in from this direction create and control both forms of quantum noise. The vacuum fluctuations come in, they go through that beam splitter, they produce fluctuations that go up in one arm and down in the other, which is the same thing as a gravity wave does, so they're dangerous. And they beat against the laser light, which it comes in and it produces fluctuations that go up in both arms together, so it's not dangerous. But it beats against the laser light to produce fluctuating light pressure that actually controls the mirror's fluctuations. And coming back out, those vacuum fluctuations that entered, they beat against the outgoing signal light to control the shot noise. And it's as though you had perfectly designed these instruments so you had just a perfect channel, one absolutely perfectly designed channel to enable vacuum fluctuations to, in fact, the quantum states of the centers of mass and of the signal light are controlled by the quantum state of the vacuum fluctuations. And this is incredible. I mean, we never imagined that, that there are these things that are a handle on the quantum noise in the interferometer. All the quantum noise, you have a handle on it in the form of these vacuum fluctuations. If you can manipulate the these vacuum fluctuations appropriately, then maybe you can send all the quantum noise into directions where that quantum noise no longer plagues the gravity wave measurements. And that's what, in fact, Carlton Caves figured out that you can do. You need to, and I'm just going to use the word, squeeze the vacuum fluctuations in what is called a frequency-dependent way. And with a little help from Bill Unruh, he was able to show that, in fact, if you do that, then you can guarantee that all of the quantum noise goes into places that don't plague your gravity wave measurements. Jeff Kimball down the hall invented the technology for doing the squeezing that Carl said you had to do. The LIGO team perfected that technology over a period of 30 years. That technology is now in place. It's called quantum precision measurement technology. After 40 years of development by the LIGO team, it's now operating in LIGO. And it is one key to LIGO today, seeing several collisions of black holes each week, compared to one every 6 weeks when we first turned on. And this goes hand in hand with quantum computing and other areas of quantum information science. And it really is the technology of the 21st century, the big technology of the 21st century, quantum technology. And it was needed for us. We knew we were going to need it when we got to this level of sensitivity. We have it, and it really is central to the future. And for me, it's really quite incredible that this understanding of vacuum fluctuations that I got from Zeldovich when I met with Zeldovich back in 1970. It was, I have to remember, it's 71, I think it was, that I went with Stephen Hawking there. That understanding turned out to be key to so much that goes on in the universe, but also key to modern 21st century quantum technology. Thank you.